So we can actually run, design the processor and run this simple subset of the instruction set architecture that shows most aspects. Like we will be running R-type instructions, including these add, sub, and or. Similarly, memory reference instruction and branch instruction, we will only be focusing on branch equal, okay, for the architecture that we are going to study. So just to quickly recall the instruction format, you see all the fields are always at the same location. So opcode will always be from bit number 0 to 6, okay, the right 7 bits, rightmost 7 bits. Similarly, RD is always placed wherever RD is needed. It is always placed in bit number 7 to 11, and you can see this is again a 5 bits field. Here in store instruction, we do not need RD. In SB branch instruction, we also do not need RD. So that is why RD are not present in this field. Similarly, RS1 is placed at the same field. RS2 is always placed at the same field. Okay, so that is why we can actually pick bit number 15 to 19 for RS1 and tie it to one of the input ports of register file here. Okay. So how are the instructions executed? Once we know this instruction format, we should know how the instructions are executed. To ask these questions, again, we need to, let's take an example of this simple instruction set, where assume that we have these set of instructions. So you should ask yourself, how does the processor get the instruction and get the operands, obtain the operands, generate the results, and save the results. So in a processor, we have these main components in order. Okay, so the hardware contains, first of all, the instruction memory. The first comes the instruction memory. Why? Because in order to execute the instruction, you need to fetch the instruction. What do you want to execute? Which means that the instruction memory should always come first. Okay, so after executing the instruction, let's say if it is R-type instruction, let's say add instruction, what should be the next step then? In the add instruction, what should be the next step? Add R1, R2, let's say R3. What should be the next step after reading the instruction? Yep. Huh?
Loading.
Loading?
Yeah.
Loading what?
One of the registers into memory.
In add instruction, do you load register in memory?
I thought you meant to say after.
Yeah, so after extracting the instruction, after reading the instruction, what do we need to do? Perform the addition, but before performing the addition, you need to identify where do you want to perform the addition, what contents. You need to read the contents, right? Contents of the registers, which means that you should go first into the register file. So once the instruction is read, the instruction is decoded, and then what happens is we provide those RS1, RS2 field into the register file. Okay. So what happens is the instruction memory and then the register file. In the register file, we read the contents, and then comes the ALU where we perform the addition operation. Okay, it computes the result. So in R-type instruction, ALU is used to compute the result. We do not need data memory in R-type instruction. Rather, we read RF again. We need to access the register file again to write the data back into the register file. Okay. So this is the execution flow of R-type instruction. So here again the same example that I just gave you. So add instruction is fetched from instruction memory using the address and program counter. So suppose we wrote a program, a Python program for example. Okay, it is then converted into an assembly code through the compiler, and then the assembly code is then converted into machine code with the help of an assembler. Okay, now this machine code is stored in a memory, instruction memory. Okay, now to execute that program, PC, the program counter, would be pointing to the first instruction of that program. Okay, and that program counter could be like, let's say the first instruction is placed at address 100, for example. So the program counter, the PC, would be containing a value 100. Okay, and then it will fetch that instruction and it will increment it by 4 to execute the next instruction. Okay, so once the instruction is fetched, the register RS1 and RS2 are read from the register file, which looks like this. And again, you will see only this block now onwards. As I mentioned that we have already discussed the internal details in past, but we will not be going into that details again. Okay, after fetching the contents, we perform the addition operation using ALU, and then the results generated are returned back to the register file at the specified register where do we want to read. Okay, in load and store instruction, again the format would be same. Instruction is fetched from the instruction memory, then passed through the RF register file. So ALU in memory instruction, what is it used for? To compute the address. Remember, LW SW instruction, we have the immediate value as well as the base register. You remember the format of LW and SW instruction? So the format is where LW, let's say S1, some offset, and then S2, right? So this is the base register, base address, and this is the 12-bit immediate value. These two are added together. And who performs this addition? ALU is performing this addition. Okay? So in these type of instruction, LW or SW, the addition, ALU performs the addition not between two register content, rather between one register content and one immediate data value. Okay? And then after reading or writing, depending on what type of instruction, we access the memory to read or write the data, and then write the values in the RF in case of load instruction. Finally, the branch instruction. Here, ALU is used to compare, and in this phase, it updates the program counter value, depending on whether the branch condition satisfy or not. Okay? It does not use the data memory. In this phase, rather, it performs this updating the program counter. All right, so let's have a quick overview of how the,
What's the difference between the first RF and the second RF?
So RF is same, it's a register file. In this phase, we are reading the registers, okay? And here, we are writing the registers back. So for example, in the case of add instruction, so first of all, we need to fetch the, let's say hit here. If this is the instruction add, let's say S1, S2, S3. So first of all, we need to fetch the contents of these register. In order to fetch, we need to go to RF, okay? And then it performs the addition between these two contents through ALU. And then it has to write the results back again to register, which means that we are again accessing the register file. Okay, so first time we access to read, second time we access to write. Okay. All right, so let's have a quick overview. It's just a bird's eye view of the processor, but we will gradually develop the processor as an activity. What you are looking at it, you are required to be doing the same thing in your activity, but this is just an overview and without including the correct details. So this should be the pathway to execute the instruction. First of all, first comes the instruction memory. Okay, whatever address of the instruction is provided at the input, it will fetch the corresponding instruction. Okay, once the instruction is fetched, again, you do not need to memorize this diagram. As long as you understand the flow, you would be able to reconstruct it yourself. Okay, understand the flow. The instruction is always fetched first. Okay, once the instruction is fetched, it goes into the register number. So register number could be RS1 register number, RS2, and RD. Okay. Once the register numbers are specified, the corresponding data are placed here. Okay, and the two inputs of the ALU. Okay, so ALU performs some operation and either generate the result, which should be written back to register in case of R-type instructions, or it generates an address to fetch the data from memory. Maybe it is the LW instruction, we provide the address, it fetches the data from the memory and write it back to the register. Okay, do you understand the flow? How is it executing the instruction? What do you think this is coming from? So first of all, this is value to write to RF. It could either be coming from ALU or it could either be coming from data memory. What do you think? Or what about, first of all, let's talk about this one. Which instruction will be writing the data to memory and why it is coming from registers? There is only one instruction, yes, the store. Okay, store instructions write the data into memory and the data comes from the register, of course. Okay, so this is data written to the memory. What about this one? What is it implying? The ALU data, the second source of the data, could either be fetching the data from register or from something else. Immediate value. Okay, that's what we just have discussed. But it is not. It would not be appearing like this as shown in this diagram. There are some details that should go in there because according to this diagram, we are just fetching the 32-bit instruction and providing it as an input to ALU. It has to pass through a certain component which we have just discussed to fetch the immediate data. Okay. And what about this one? How do we increment the counter, the program counter? As I mentioned that we will be using some components like an adder, simple adder, which will help us increment the program counter. So the program counter contains the address of the instruction, the next instruction to be executed. Okay, so whatever the address will be provided here, that corresponding instruction will be executed. It will not only provide the address here, but the address will also go into the adder and it will be added by 4 to increment the next instruction's address by 4. Okay, so here is the one which will be containing the next instruction address. And what about this one? What do you think it is calculating? It is calculating the branch instruction. Again, the details are not mentioned in there, but the current address plus the label address would actually give us the branch target address. Remember this format of branch instruction. Here we have BEQ, let's say X1, X2, and then let's say label. And we have some instructions, maybe label is pointed here. So PC is currently pointing to this one. So this address plus the label value, whatever the value of the label is. And this is actually an offset. This is not an instruction. This is an offset defined by the 12-bit immediate value. We have already talked about this when we were discussing the branch instruction. Okay. Okay, so yeah, so this is the next PC. So here you see there are multiple sources of data coming in these pathways, these 3 pathways. It just looks like two-way multiple way of traffic signal. The traffic is coming from 2 directions, and if we do not have a traffic signal in between, they would collide each other, right? They bump into each other. So how do we control this? mux. So thank you. So mux is a component that we use to output one of the many inputs, to connect the output to one of the many inputs. So here we need an output, mux, which will decide whether the data should be coming from the ALU or the data memory. What data should be written into the register file. Okay. Similarly, this mux will decide whether the addition should be performing between the register contents or the data coming from the immediate field. Similarly, this one will decide the next instruction is actually in the instruction which is in sequence, which is in order, which is the PC plus 4, or the branch instruction. It will decide which instruction to be executed. Okay. Any question here? So this is the actual diagram. Again, it has some missing components in it. You can see these are the muxes placed at this in this diagram, and it will remain there. Okay. So whatever we build on top of this diagram, the muxes will remain there. So we have these some control signals: the ALU operation, reg write signal, mem write, mem read signal. Where do you think these signals will be coming from? So who will decide whether we need to write the register, whether what operation we need to perform, or whether we need to read the memory or write the memory? Opcode. So based on the opcode, we need to decide what operation we need to perform and which things can be set to 1 or set to 0. Okay, but there is a specific unit which we call control unit. So that control unit has a separate circuitry. We haven't discussed the details of that one, but just assume that we provide the opcode field here, or just assume that we are providing the instruction here, and based on the opcode or based on the instruction, it will generate the signals accordingly. Okay, so for example, if it is R type instruction, add instruction, what do you think the value of this signal be? Reg write signal. If it is an add instruction, okay, what do you think the value of this signal would be? Reg write. 1 corresponds to we want to write the register value, and 0 corresponds to we do not want to write a register value. Hmm? 1. Why? Because we want to write the results into register. So that is why reg write signal, this control circuitry will set this value to 1. Okay. Similarly, what will be the value if we it will also decide what value should be selecting this input or this input, depending on what type of instruction it is. It will decide whether the data is coming from the register or from the immediate data. Here, this appears to be incomplete. This mux actually controls whether the next instruction to be executed is the one which is in order or the branch instruction. So again, if you recall, what does the 0 signal correspond to? The 0 signal tells that the result is 0 or not. If it is 1, it means that the result of these two inputs is 0. Okay, it performs the subtract operation and it generates the 0 signal. If it is 1, it means the result is 0. If it is 0, it means the result is non-zero. Okay, so the control unit again identify based on the opcode. It will generate this signal which identifies that it's a branch instruction. Okay, if it is a branch instruction, this value will be 1. This wire will contain a value 1, and 0 signal generating from 1 would signify that the branch instruction the branch is taken. Okay, the branch condition satisfy. So it should be an AND gate. So this AND gate, when both these two inputs are 1, it will set this value, output value, to 1, and then this input value of the mux will be selected. Okay.